We may start. Hello, everybody. Thank you for coming back to this course. We took a major step last time by proving the Morse Theorem, which enables us having any k which is bigger than or equal to 0 on a set, which sometimes we write omega for the set, sometimes x. In the next chapter, indeed, I will mostly write x due to interpolation. Whenever such a k is given, then Morse theorem says that there is a reproducing kernel Hilbert space, H, which we denoted by H of k, because its kernel is precisely k. And based on a simple proposition that we had before the Morse theorem, this construction is unique in that there is just one RKHS with this property. And now we started already to study the effects of K on H. The first one, I mentioned as recall. The first one was that if K is a continuous function, omega times omega to C is continuous, it implies that every f in H of k is continuous. And indeed, we used a result in the proof, which by itself is somehow important, that if xn, or well, better to say xi, when I is in a set I, is a net, and xi or x iota converges to x in omega. We assume that omega has a topology. So it's a generalized way of thinking about convergence here. If you have a convergent net in X, then the corresponding kernel function k x iota converges to kx in the space H. So this is something that we used in the proof to show that the elements of H are continuous, but by itself is important to recall. Now we continue this. From here, we have new results. The first one is about taking the conjugation. If k is given and k is bigger than or equal to 0, with the meaning we gave, every n by n matrices formed with n distinct nodes is a positive matrix, then we can define L of x and y to be k x and y bar. It's very easy to see that L is also positive. I will show in the proof of next proposition. L is also positive. It's easy to verify. We will do. And so we can talk about H of L. So what is the relation between H of L and H of K? Because of the bar, it is easy to guess, or it's expected to have that this is precisely equal to H of K bar. We take conjugate of all elements of H of K, and we obtain another space. This is true. It's a good expectation, and I prove it in this proposition. Let k from, let's switch to x times x in C, be a kernel function, which I briefly wrote as this one, bigger than or equal to 0. It means equivalent to say it's a kernel function. Then L equal to K bar is also a kernel function. And we have what is written here. The space generated by L is the same as a space generated by K, take bar of all the elements. Moreover, we can have a map, a very natural map, C, defined from one to the other, for example, from H of K to H of L, sending F to F bar, is a surjective conjugate linear isometry. Surjective is kind of trivial from the definition. Conjugate linear also kind of trivial from the definition, but the isometry part, it has to be verified. You shouldn't say that when we calculate the norm of F is equal to the norm of F bar. Of course, for many function spaces and spaces that we consider, this is the case, because I mean, there is an absolute value somewhere. Usually we use an integral formula. And in the integral formula, there is an absolute value. So there is no difference between F and F bar. But in general, we do not know. And this is something that has to be verified. Proof. First, why L is a kernel function. For this, let x1 up to xn be in X distinct. And correspondingly, n scalars, not necessarily distinct, any alpha 1 up to alpha n in C. Then what can we say about the sum I and j from 1 to n, alpha I, alpha j, L of xi and xj, and we need to put bar somewhere, either on the first one or the second one, doesn't matter. Sometimes it is more convenient to put it on the first one, but it's the same. We need to show that this combination is positive. That's the meaning of being a kernel function. And immediately we see that this is equal to sum a and j from 1 up to n, alpha bar, alpha j, k of xi and xj. That's the bar. That's the definition of L is k bar. And now I take bar out, means that sum a and j, both of them from 1 to n. The whole thing bar. And the whole combination inside the parentheses by the assumption that k is a kernel function. By this assumption, inside is positive. So the whole thing here is positive. So this means that L is a kernel function. That's very easy. And note that little l of x, which is defined by the formula k of y, L. L of y and x. That's the definition. So this is the definition of little l of x. And by assumption, this is k bar of y and x. So this is assumption. And again, I use one more time the definition. This is equal to little k x at point y bar for every y in the space x. Again, this is the definition of little k. And we see that immediately little lx is equal to little kx bar for every x. That's the simplest manifestation of what is claimed here. What is claimed here is that the element of HL are the conjugate of element of HK. So here is one incidence of that. L of X is an element of space HL, and K of X is an element of HK. And by definition, we obtain this. And the rest is just a linear combination of both sides, and then taking the limit as analysts do. Here is the way to do it. So that's one thing to do. The other thing, which indeed is an outcome of this, what is the inner product of Lx and Lx prime, say, in H of L? So let's calculate. This is Lx at the point x prime, the meaning of kernel function, which is equal to the capital L x prime and x. That's the defining relation between capital L and small l. By definition, this is k of x prime x bar. And we do the same identities we did for L in reverse order for K. So, so this is little k x at point x prime with a bar. And that is kx prime in H of k bar. And having the bar, we can change the order, right? Kx prime, kx in H of k. This is an important identity, the relation between H of L and H of the inner product in HL and the inner product in HK. I write it again, a box formula. So L index x, inner product with L x prime in H of L is equal to the order reversed, kx prime kx, inner product in HK. This is a consequence of indeed this identity, and also will help us to establish this. Let's see how we can do that. First step is the definition of C on a dense set, precisely as we did in Morse theorem. So definition. We define C of the sum j from 1 to n, alpha j k, say yj, to be sum j from 1 to n, bar of this, say alpha j bar, and kyj bar is lyj. That's my definition. How to show that? I mean, this is well defined because this is an element of this space, but the representation is not necessarily unique. I mean, F, which is of the form j from 1 to n, alpha j k yj, it might also be of the form a from 1 to m, beta I, say k zi, with another set of points. We have seen incidence of this before. If there is a linear dependence between kernel functions, this is possible, like the third and fourth example in Sobolev spaces. In the third one, K0 was equal to K1 equal to 0, both of them, so two linear dependence here. And in the fourth one, K0 was equal to K1. So one dependence. And many more combinations in more sophisticated spaces are possible. So briefly speaking, F might have several combinations like this. And when we define C, we might use this combination. So it gives us one C of F with this one, and another formula with this one. And in the general setting, there is no clue that these two are the same. If not, it's not a good definition. And we saw this indeed in Morse proof too. And we showed that it's well-defined, there is no problem. In the general setting, you need to consider an identity like this, which is like this, and calculate C of F using the first formula, also C of F with the second formula, and show that they are really equal with some techniques. One of the techniques which in many occasions help us is to show that there is an isometry between the function which is here and the function which is in the image. In other words, if I can show that the norm of j from 1 to n alpha j k y j in the first space is equal to the norm of its image, which I wrote as sum j from 1 to n alpha j bar L of I j in H of L. If I can show this for any combination, any linear combination with the different alpha j, that is enough, because you take the difference here and you have a combination such that it's equal to 0. So its image is equal to 0, which means that in the combination, C of F, call it C1 of F minus C2 of F, its norm is equal to 0. So they are equal to each other. So if whenever you show an isometry like this, I emphasize this because it will happen in future lectures too. Whenever you have an isometry like this, the definition is fine and we can proceed. And now it is easy to show this, this isometry based on this, the green, or this one, based on this box formula. It is easy to arrive at what I want. So this box formula is also, which is consequence of the previous one, is useful for us. Let's calculate the norm squared. So sigma j from 1 to n alpha j k y j squared in H of k is equal to, well, it's inner product with itself, j from 1 to n alpha j k y j, and sigma, I use another index, I from 1 to n alpha I k y I in H of k. It's linear. We can write it as sum over I and j, alpha I bar, alpha j, k y j, inner product with k y I in H of k, which we know it's equal to, here it is, the inner product of the corresponding function in L, but the order reversed. So this is equal to, I can put identity here, indeed, it's better to put it there. Alpha I bar, alpha j, L yi, L yj in H of L. And I do the same operation in reverse order, means that I put the coefficients inside and sum. So now I have sum I from 1 to n alpha I bar L of yi, and alpha j goes inside, it becomes conjugate sum j from 1 to n L yj in H of L, and these are the same. So it's become same sum j from 1 to n alpha j bar L of yj norm squared. And this is precisely what I wanted to obtain, the isometry. The isometry, this one, which is what I wanted indeed to prove. C from H of k to H of L, mapping F to Fr, and such that C of F in HK, in HL, is equal to the norm of F in HK. I did not do for all elements, but I'm not far away from the end, because what I proved here is that this is true for all F of the form sum alpha j k yj. And the good thing is that we know this, call it W as in Morse theorem. W is dense in this space, and its image is also dense in H of L. And the rest is just taking a limiting argument and using the fact that convergence in norm implies pointwise convergence. In other words, you can see an arbitrary f in H of k, not necessarily of this form, but there is a sequence, I call it Fn, in W, such that Fn goes in F in H of k. W is the collection of all functions of this form. And by isometry, I'm sorry for that. We know that we know that if n is a Cauchy sequence to n, so C of Fn is also a Cauchy sequence, and then the fact that C of Fn converges with my apologies, implies that and the fact that C of Fn is equal to Fn bar, this we have already shown. Both of them implies that, and also don't forget this, that C of F is equal to F bar. I mean, it's a little detail that I leave it for you to complete. But the bottom line is the fact that convergence in norm imply pointwise convergence, and that is why we obtained this one here.
Sir,
Yeah.
Is this space HL isometrically isomorphic to the dual of HK?
We can make a mapping. I mean, it's not mentioned in this way in the proof, but we have, if you wait, not our next example, not the third one, the third example that, or the set proposition that I will study today is about Rkhs induced by inner product. And in that, we will see precisely what you mentioned. So wait a little bit, we will arrive at that result. Hopefully today. Our next Rkhs is Rkhs induced by just one function. We saw this before, but there is one more item in the result that I want to highlight. So Rkhs produced by one function or by a function. We will need this in a future lecture too. So proposition, X is a set, and f is any function on X with its value in C, f not identically equal to 0, just a non-zero function. Even it might be non-zero at one single point and 0 everywhere else. So, and define, so put k of X and Y to be f of X, f of Y bar. Then we saw before k is a kernel function. At least I mentioned this. What is new is that and h of k is indeed a one-dimensional space, is equal to C times F. One-dimensional vector space. And in this space, for sure, F is there, normal F in this space is equal to 1. It's normalized that way. We will need this result in future, even though it's elementary. That K is a kernel function is very easy. As before, we fix some points and study what is sum ij from 1 to n alpha I bar alpha j k xi xj. What is this? So we have the formula for k, we plug it there. So sum alpha I bar alpha j f of xi f of xj bar. That's the definition of k. And now we immediately see that this sum can be written as the sum I from 1 to n alpha I bar f of xi, the whole thing absolute value squared, which is positive. So it's a kernel function. And what is the little k here? Little k at point y, k of y, by definition is k, y, and x, which is equal to f of y, f of x bar, by definition. This is true for every x come as our argument in the space. So the same identity can be written this way. K of y is equal to a constant. No, wait a minute. There is something. Oh, I see my mistake. I see there is something wrong. There shouldn't be bar on this. My mistake is precisely here. my mistake is that k of xy is x here, y there. So it will be fx, fy bar. And x is the argument. So this identity can be written also as ky as a function is equal to a constant times the function f. So it's just one function with different multiples. And if you remember the space W, the space W was the space of all linear combinations alpha j, k, y, j, with different values of alpha j and yj. But it doesn't help that much. I mean, if you consider different values of yj, it gives you different coefficients here. And you multiply by alpha j, that's another coefficient, and sum them up is still another one. So at the end of the day, when you consider all different yj and alpha j, you obtain nothing but c times f. And c times f is already closed. So the space is precisely this one. It's one-dimensional. So h of this kernel function is precisely CF. And how can we calculate the normal f in this space? It's very interesting trick. I mean, playing with all different identities we have seen by now. On one hand, we know that k of y is equal to ky, ky, which is equal to the norm of ky squared in the space. And now let's see what each side gives us. For the norm of ky is calculated here, is the norm of fy bar as a coefficient time f. So the coefficient comes out and the function stays. And this is precisely what we want to calculate. We want to calculate normal f. So that's what this part gives us. And now let's see what is k of y. By definition, the very original definition, k of y is f of y bar. At the very beginning, we defined k of x and y to be f of x, f of y bar. So it's absolute value of f of y bar. And now compare these two using this identity. You immediately see that. So absolute value of f of y squared, normal f squared is equal to f of y squared. And now this is for any y. This is the point you see I emphasized f is not identically equal to 0. So at least there is one point such that f of y is not 0. And we can eliminate f of y from both sides and deduce that normal f is equal to 1. That's what we wanted to prove. It's a very specific RKHS, but it will appear in our discussion near future too. Another example is an interesting one with applications in economic, the mean function. We define k on 0 infinity times itself with values in R by a very simple formula. K of x and y to be the minimum of x and y. So K lives here, and that's the frontier. In this neighborhood here, K is equal to X, and here K is equal to Y. And on the diagonal, they coincide. Immediately, you see that I haven't shown that it's a kernel function yet. I need to do a little bit of work, but at least in advance, you can say that h of k consists of continuous functions because k is continuous. We'll see some of its element later on, but at least from k continuous on 0 infinity. We can immediately, you see that the importance of that theorem, without knowing what is in the space, in advance, we can tell that h of k consists of continuous functions. That's the power of that theorem. But I mean, before arriving at this, we need to show that K is a kernel. It's not as straightforward as the examples before. We need to do a little bit of work. And for that, let me introduce this matrix Gn, which is an n by n matrix. All of its elements are 1. We need this one. And the lemma about this is that lemma Jn is positive, bigger than or equal to 0, and has eigenvalues, and sigma is a notation which we use in operator theory, but in matrix analysis it's just eigenvalues. Sigma of Gn is just 0 and 1, but with different orders. The eigenvalue at 1 has multiplied, let me read here. Gn, every other eigenvalue, Gn is 0. Okay, it's not mentioned in the lemma, but the order of 1 is 1, and the multiplicity of 1 is 1, but the multiplicity of 0 is n minus 1. This is, it's not explicitly mentioned. So multiplicity of this one is n minus 1. This one is equal to n. It's not explicitly mentioned in the theorem. And there are many ways to prove this lemma. It's usually the case with resulting linear algebra. Many elegant proofs exist to show the same thing. For positivity, the most straightforward is, as before, to calculate that sum.
Robin, can I interrupt? I'm misunderstanding something. This is the matrix of all ones?
Yes.
Aren't the eigenvalues 0 and n?
Yes, thank you. Yes, n, 0 and n. Yes, indeed. Yes, indeed. I will add in the proof I added here myself by hand. I written the determinant of lambda minus Jn is lambda exponent n minus 1 times lambda minus n, which makes this correction. Thank you for pointing this out. So it's 0 and n. So the proof for positivity is, I mean, the straightforward proof that we use all the time for any v in Cn, or here Rn, but we have to do it for Cn indeed, even if the matrix is real for Cn. What is the sum? Sum I from 1 to n, j from 2 n. That sum is precisely Gn of V inner product with V in Cn. True. And if you write it more explicitly, this is A, I, and G from 1 to n, then alpha I bar, alpha G bar times the Ig element of Jn, which is all the time equal to 1. And, oh, no bar here. And we see immediately that, as we saw before, this is the absolute value of one of them, for example, j from 1 to n alpha j, squared in absolute value, which is positive. So this shows that it is a positive. And to show that it has just two eigenvalues, one way, as I said, is to calculate determinant of lambda I minus Jn. And it's an easy exercise to see that this is lambda exponent n minus 1 times lambda minus n. So I let you to do it directly. I mean, it's not something difficult. Another one is to give explicitly the eigenvalues and eigenvectors. For this matrix is easy. V1, all its element coordinate equal to 1. And we see that Gn of V1 is equal to n V1. So it shows that n is an eigenvalue and V1 is an eigenvector. And to show that we have also 0 as an eigenvalue, I give you other vectors. V2, you put 1 here and minus 1 there and 0 for the rest. V3, you shift this down. And finally, you arrive at 1 minus 1. There are n minus 1 of them, clearly independent. And for each of these, you immediately see that Gn Vk is equal to 0. So they are in the kernel and show that the kernel has dimension n minus 1. The other dimension is for the eigenvalue created by V1. Why do we need this? Is for the kernel created by the min function, and here is the proposition. K defined on 0 infinity times 0 infinity to r by kxy is a kernel function. So what do I need to prove? Oof. I need to consider endpoints. So let x1, x2, and xn be in the space x. X is here 0 up to infinity. And I need to consider the matrix K, x1, xi, xj, this n by n, and show that this is bigger than or equal to 0. And what is this matrix? It depends if comparing x1 and x2, comparing to them, which one is smaller? And k of x1, xi, xj would be eventually either xi or xg. So I have a matrix like this, and the component ej here is eventually either xi or xg, depending which one is smaller. So to give it a bit of order, we can say, without loss of generality, x1 less than x2 less than x3 and up to xn. And even if they are equal, it really doesn't matter. But why without loss of generality? In general, and it's an important point to consider this, when we look at the original definition, we do not assume this. Indeed, there is no ordering when we consider an arbitrary x. We consider endpoint, and sometimes we emphasize that they are distinct. Here, even if they are not distinct, that's not a big deal. But still, we cannot assume in advance that x1 is less than x2, x less than x3. So there is no ordering. But why still I can say that without loss of generality, this is true. This is again based on our knowledge of linear algebra, and because if P is a permutation matrix, it means that it's a matrix of this form. All elements are 0 except at the intersection of 2 rows and 2 columns. Here we put 1 here, 1 here, and all of course on the diagonal is equal to 1. Here is 0, here is 0, on the diagonal 1. And all other elements are equal to 0. So it's kind of permutation between either row I, row j, or column I, column j. I can call it Pij for further reference. So the question is for you, if you're not familiar with this matrix, what is Pij multiplied by a matrix A from the left side, or we multiply from the right side? What is the consequence? It is easy to convince yourself that if you multiply from the left side, the outcome is the same matrix, except that you change the row I with row j. You just change the ordering. And the same thing with the other one. If you multiply from the right side, then the columns are changed, but just column I with column j. And another thing to notice is that Pij inverse is the same as Pij, and of course is equal to Pij star, is self-adjoint. And the final thing we need here is that A is bigger than or equal to 0 if and only if Pij A Pij is positive. In other words, you can multiply it from both sides, left and right, by Pij with any I and j you wish. And that's the clue. That's the clue for what I wrote here. That's the clue for what I wrote here. Of course, at the very beginning, x1 might not be the smallest one, but we apply this observation here. We multiply our matrix by Pij with right choice of I and j, such that we can bring the smallest one at the very beginning. And what would be the consequence of this? If we do this, if x1 is the minimum of x1 up to xn, and we apply this transformation, then k x1, xi, xj, this n by n matrix will start like this. Because it's the smallest one. Here still we do not know. We'll consider later. So by bringing x1 to the very beginning with this transformation, we have this formula. And then we do similarly with the second smaller one. We multiply from both sides. And note that if we change, say, row I with row j, here it really doesn't matter because it's x1. And the same for column I and column j, when we change it, is x1. So it doesn't affect this part which is already taken care of. We improve the rest. And so we continue up to the end, and we obtain x1 less than or equal to x2 less than or equal to xn. And if we do all of this, we will see that at the end, when we do all this modification, our matrix has this form. Then here is x2. Then about this is x3, and we continue up to xn here. In other words, and this broken line is a constant. And finally, we have xn here. And this way, it's easier to show that we have a positive matrix, because you immediately see that if x1 is less than or equal to x2 less than or equal to xn, I can write this matrix as x1 times jn. So if I subtract x1 from the previous matrix, this is equal to plus. Plus what? If I move this to the other side to see what is my matrix here, x1 times jn is a matrix, all of its elements are x1. So here I would have 0. And here x2 minus x1. After this x3 minus x1. And finally, xn minus x1. And now you see up to here, it wasn't that clear why I consider 0 up to infinity. Why just positive ones? It's more transparent here now. Jn is positive. We multiply by a positive coefficient. So the whole thing is positive. This one is also positive by induction. I mean, we start with n equal to 1. N equal to 1 is just, k x I x j. If we consider 1 by 1, it's just x1. And again, this is another indication why we consider 0 to infinity. It's something positive. So we have a positive matrix here. We have a positive matrix there. We add them up. And the conclusion is that kxi xj for any n is positive. So we have a kernel function. Now we want to, we have a break now. After the break, we try to detect some of the elements of this space.